You're sitting on a plane, thousands of feet in the air, looking out that little window, and have you ever just stopped and thought, how is this actually working? I mean, what invisible magic is holding this giant metal tube up? For more than 100 years, the answer to that question has been at the center of a pretty intense debate. So today, let's finally put it to rest and solve the great lift mystery.
In one corner, we've got Daniel Bernoulli and his famous principle about fluid pressure. And in the other corner, the legend himself, Sir Isaac Newton, with his unbreakable laws of motion. So who got it right? Who's the real champion of aerodynamic lift? Well, as you're about to see, this isn't about picking a winner. It's about understanding how they both fit into a much bigger, much cooler picture.
You know, instead of this being a fight to the finish, what we really have here is a classic case of two people describing the same event from different angles. It turns out Bernoulli and Newton weren't enemies at all. They were actually talking about two sides of the very same coin.
Okay, let's break this down. From Bernoulli's point of view, it's all about what the air is doing to the wing. You have air moving faster over that curved top surface, and that speed creates a pocket of lower pressure. Higher pressure below, lower pressure above, and whoosh, the wing gets pulled upwards. Newton's camp, though, they're looking at it from the exact opposite perspective. What is the wing doing to the air? The wing is tilted, it's physically pushing air down. And for every action, there's an equal and opposite reaction. Push air down, and the air pushes the wing up. Simple as that.
All right, before we go any deeper, we have to address the elephant in the classroom. A lot of us were taught this thing called the equal transit time theory. You know the one, two little air particles split at the front of the wing and they just have to meet up at the back at the same time? Well, that's just not true. It's completely wrong. The air on top moves way, way faster than that theory would allow. So let's all just agree right now to toss that idea out the window so we can get to the real physics.
So, if Bernoulli and Newton aren't fighting, how do they actually connect? Well, to get that, we need to wrap our heads around a really fundamental idea. For our purposes, air is a fluid.
That's right. The air you're breathing right now, to a physicist, it behaves just like water. It flows, it deforms, it follows all these elegant rules of fluid dynamics. And understanding that air acts like a super thin, invisible ocean is the key that unlocks this entire puzzle.
And here it is, the big connection. You simply cannot have Bernoulli's pressure difference without also having Newton's downward deflection of air. They aren't just related, they are two effects of the exact same cause. They are, for all intents and purposes, mathematically handcuffed to each other. One cannot happen without the other.
But that still leaves a pretty big question, doesn't it? Why does the air follow the curve of the wing so perfectly? What's forcing it to behave in this magical, lift-generating way? Well, this is where we find the real secret ingredient. Something I like to think of as the no U-turn rule.
Now, the official fancy name for this is the Kutta condition, and really, it's just a simple observation about how the universe works. It says that when air flows off the sharp back edge of a wing, it has to leave smoothly. It can't make a crazy, sharp U-turn. Nature just doesn't like that.
Let's walk through this. So in theory, air could try to whip around the trailing edge of the wing in this physically impossible turn. But air has this tiny bit of stickiness, called viscosity, that just says, nope, can't do that. So nature has to find a workaround. It fixes the flow so that it leaves that edge nice and smooth. And the result of that fix? It creates this beautiful, stable swirl of air around the entire wing. We call that circulation.
Okay, so we have all of our pieces on the table now. We have the Kutta condition, we have circulation, and we have our old friends Bernoulli and Newton. Now, let's put it all together and see the complete chain of events that makes an airplane fly.
And here it is, the whole cascade. It all starts with the Kutta condition, the enforcer. It demands that smooth flow. That demand creates the swirl, or circulation. That circulation is what makes the air go faster on top and slower on the bottom. And that's where Bernoulli steps in, turning that speed difference into a pressure difference. And what's the overall result of that entire system? A massive amount of air gets deflected downwards, which gives us our big Newtonian push upwards. See? It's a perfect, logical domino effect.
And get this, this isn't just some abstract idea, it's real hard math. The Kutta-Joukowski theorem is basically the golden equation of lift. It lets us calculate L, the lift force, by directly using gamma, which is the strength of that circulation. Engineers use this to predict with incredible accuracy exactly how much lift a wing will make. It's amazing.
So we've pretty much cracked the code for how planes fly below the speed of sound. But what happens when you decide to just throw all those elegant rules out the window and go faster than sound itself? Well, that's when a whole new world of physics kicks in.
At subsonic speeds, the air gets a warning. Pressure waves travel ahead of the wing, kind of like saying,
excuse me coming through. But when you go supersonic, you're literally outrunning your own sound. The air has no idea you're coming. It gets slammed, totally surprised, creating these incredibly powerful shock waves. Lift is no longer about smooth, elegant flow. It's about brute force and violent compression.
And this changes absolutely everything about how you design a plane. Wings now need razor-sharp edges, basically to pierce the air. The point where lift is focused, the center of pressure, jumps backward dramatically. That's a really dangerous thing called Mach tuck. The whole game changes from trying to coax the air smoothly to just managing these violent shock waves.
This analogy here just says it all, doesn't it? Flying subsonic is like a boat gliding through water, creating these gentle, smooth ripples. Flying supersonic is like a bullet smashing through a sheet of glass. The air doesn't flow, it shatters. It's physics by impact, not by persuasion.
So the great debate between Bernoulli and Newton, well, it was never really a debate at all. They were just two parts of a single beautiful and complete picture, all held together by nature's simple rule against making U-turns. We've seen how that all falls apart at supersonic speeds. So the question I want to leave you with is this. As we push even further into the hypersonic realm, we're talking 5–10 times the speed of sound, what new rules are we going to discover? And how will everything we know today have to change to meet that next challenge?